Bailey, who is a tenured full professor and vice chair of research in the Department of Family Medicine here at ETSU. She has a Ph.D. in developmental psychology from Wayne State University in Detroit, Michigan, and was on the faculty there until she came to ETSU in 2003. And she is an expert in research and research methods and all things statistics. Her areas of research include maternal and child health and issues like pregnancy, smoking, intimate partner violence, breastfeeding, and other topics. And she has several pages of peer-reviewed research publications. Some of her current grant funding include a 5-year HRSA grant that our Department of Pediatrics is participating in for providing team-based care in the primary care setting and training students and residents in team-based care. So we will go ahead and get started in the interest of time, but we're very fortunate to have Dr. Bailey here today, and she's going to be talking about interpreting research findings, something that we all can use help with, and some basics of statistics that every clinician needs to know. And when she starts talking, we'll just make sure if you have trouble hearing her, raise your hand and we'll get a room microphone.
There we go.
Okay.
All right. Well, thank you. Can everybody hear me okay? Are we good? All right. If not, if I fade, let me know. All right. Well, this is amazing turnout for an hour-long talk on statistics. I'm just astounded. So not usually the topic of choice for most people. All right, so what I want to talk about today is kind of the basics of what you need to know in order to be good consumers of medical literature. So when you go out and you have an article that you're trying to read, I'm going to try to give you some basics that will help you interpret. All right, my standard disclosure form, nothing to disclose. All right, so here we are starting with kind of some realities of the situation. All right, so most physicians don't have the time or inclination to become expert in statistics. True? Yes, okay, I recognize that. All right, so being a good clinician requires being aware of the latest research findings in your field. Would we agree with that? All right. Unfortunately, gaining knowledge from published studies requires a certain level of statistical expertise. Find overwhelmed sometimes when you go look at a journal article. All right, not understanding the findings presented in key studies in your field limits your ability to critically consume and apply the latest knowledge. Okay, limiting factor if you can't read and interpret those articles. All right, so a lot of times we rely on summaries. We go to databases that give us summaries of the most up-to-date literature. But those are limiting, okay? You're relying on the person who did that summary, their interpretation, what they think is important. So if you really want to be a good consumer yourself, you need to be able to read the original studies. All right, so the basis for my talk today is really from 3 papers that have come out, 2 very recently, one back a little bit further back in 2003. And basically what these studies did was they went and reviewed journal articles in primary care fields and looked at what are the key statistics that are being used in those journal articles. Okay? So they randomly selected a set of published papers, and then they categorized all the statistics that were being used in those papers. Okay, so we have 2 main things that came out of all 3 of these papers. All right, the first suggested that medical school education in statistics and epidemiology is not adequate. Okay, so in particular, they identified that a lot of papers have advanced statistics. They use a lot of epidemiology concepts that you may not have been exposed to. And there's a lot about research design that you need to know in order to be able to say, hey, this is a good study, this isn't a good study. Okay, so that was kind of the bad news. The good news, however, was that they also identified the basic statistics that if you understand will allow you to read and interpret about 70% of the studies published in clinical fields. Okay? So they made a list. So this is going to be what I will talk about today is kind of what are these critical statistics that you need to know. Okay? So we'll take a glass half full approach here today. All right, so here are the basics. These were tests that were identified in one or more of these 3 papers as the basic things that you need to know in order to be able to read journals in the primary care fields. All right, so this is kind of a list. We'll go through, I'm going to go through each one of these, and we're going to put up some tables and things so that you can see whether or not you can adequately interpret the statistics. So I want this to be interactive. I'm going to ask you questions. I do not want to talk for 45 minutes about stats to you. I want you to participate as well. All right, so these are the things we're going to, in 45 minutes, try to cover. All right, so first thing, before we get into the actual statistics themselves, we need to look at how do people who write articles or do studies, how do they decide which statistical test to use to analyze the data in a particular study? Okay, you ever wonder why a t-test versus an ANOVA versus a correlation? Okay, what do we use? What do we choose? What helps you choose? What's the #1 thing that drives what analysis you should use? Anybody? Yes, Dr. Wood. There you go. What kind of data? So in particular, what kind of data is we want to know the level of measurement of the variables. Okay? Remember that term way back when you had a statistics class? All right. So the level of measurement of the variables involved. So what does that mean? Okay? Basically, there's 2 things that we're looking for. Are the variables categorical? Do they come to us in categories? Or is it a continuous variable? Okay, so categorical can be 2 categories. It can be 3 or more categories. We discriminate because the analyses depend on that. All right, so something like gender. You're male, you're female. Okay, that would be an example of a categorical variable. Okay, race, different race categories. Study group. You get drug A, you get drug B. That would be an example of binary, 2 groups. Okay, the other type of variable is continuous. Okay, so these would be scores. And what we care about most in selecting an analysis is, are those scores normally distributed? In other words, are most of the scores in the middle with few scores in the tail, that bell-shaped curve? All right, so some examples here: blood pressure, heart rate, lab values, weight, height, all of those would be continuous variables. And so the level of measurement will determine which test you choose. All right, so in addition, we have descriptive statistics and we have inferential statistics. So descriptive statistics just describe your sample. Okay? They don't tell you if groups are significantly different, if variables are significantly related. That's where you turn to inferential statistics. All right, so let's start very briefly with descriptive statistics. We have 2 types. We have what we call measures of central tendency. Okay, these are what tell you the typical value in a distribution, or for a variable, what's the typical value for your sample. Okay, we have a mean, which is an average, which you'll see an M or an X bar, an X with a line over it. Okay, so this is you add up all the scores and divide by the number of scores. Okay, typically we assume data is continuous and normally distributed when you see a mean. Okay, a median is a midpoint, so we use this when maybe we don't have a normal distribution. Okay, so we need to be concerned with the fact that maybe our variables are very spread out, they're not well distributed, so a median will take that into account. And then finally, for categorical data, we look at things like what's the most commonly occurring value or percentages in different categories. Okay, the other type of statistics is a measure of dispersion or spread. Okay, this tells you how far values are from the typical value. So you've heard the term standard deviation, hopefully. Okay, the range, the middle one may be less familiar to you. The interquartile range. Okay, this is when we define the middle half of a distribution, and we use this with medians. Okay, if you've ever seen box and whisker plots, those strange little things, the bars with the lines coming out of them on a graph, okay, we typically use those to represent interquartile ranges. Okay, so those are your basic descriptive statistics. All right, so here is a table from an actual paper. Okay, the table 1. Table 1 in most papers and journal articles describes your sample. So that's always the place you want to go first if you want to know who participated in this study. Okay, so this is actually table 1 from the journal article that's listed down here. I know it's a little bit hard to read. I'm going to talk about 4 different studies that came out in pediatrics within the last 6 weeks. So either this month or last month, these are tables from those papers. All right, so this one in particular was a fetal alcohol paper, and it was looking at comparing babies who had had heavy exposure to alcohol prenatally and control subjects. Okay, so this is the table 1. They didn't get into the fact that they were looking long-term at their cognitive development, but simply looking at the differences between the 2 groups on some background factors, describing our sample. All right, so this will describe the central tendency and spread for the 2 groups. All right, does anybody want to tell me about this table or something we could glean from this table? What would be a good statement to describe some aspect of the table? Everybody's got their mouths full now, so it might be a little hard. All right, anybody want to make a statement maybe about maternal age? What do we learn about maternal age in this table? Okay, our 2 groups are pretty similar, right? Okay, so a statement we could make is that the average age of the average maternal age where there was heavy exposure was 27.2. Okay, what's that number after the plus or minus? Standard deviation. Awesome. Okay, you know that, and there is no footnote on this table. Okay, usually you would go to a footnote to tell you what the values mean. This table was actually published without a footnote. Okay, so good that you all knew that that plus or minus was standard deviation. Okay, what about the numbers and then the number in parentheses? Percent. So we have an N and we have a percent. So what this means in the first column, second row, the mother married percent, 26 of the control subjects were married, and this was 46% of that group. Okay, so that's how you would interpret that. All right, key thing here in this descriptive table, there's no information about whether the groups are truly different. So I asked you, and the first thing that you did was tell me, oh, they're pretty similar on maternal age. Okay, they are to eyeball it, but there's no information here that tells us whether they're truly different or truly the same, okay, because this is just a descriptive table. All right, so here's a few statements you could make about the table. Okay, so as I said, the average mother's age at delivery among those with heavy alcohol use during pregnancy was 27.2 years. Okay, that's a factual statement from the table. Okay, look at the second one. Maternal age varied more among those who drank heavily during pregnancy than among those who didn't. Okay, where did we get that information? Yep, standard deviations. Okay, notice that the standard deviation for the control group is smaller than the standard deviation for the heavy exposure group. So we can make a conclusion about who varied more. Okay, third one, those with heavy alcohol use were almost twice as likely to smoke than those who did not drink alcohol. Okay, look back. See the differences there? This would be the third row, okay, 87% versus 46%. Okay, so we can say that's almost twice as much. Compared to babies born to women who did not drink, babies born to women with heavy alcohol exposure were more than 4 times as likely to be low birth weight. Go back. Okay, this is our bottom one here. Look at the percent, 6.3 versus 28.7. Okay, so we can make conclusions about the relative size difference. We just can't say whether or not that difference is significant. Okay, and then finally, babies born to women who did not drink had higher birth weights. So this gets not just at the percentage, but the actual birth weight itself. So again, nothing about what's significant, just descriptive. All right, so a few things here. Okay, be wary of misleading presentations. All right, so the first one here, tobacco industry research, excellent health statistics, smokers are less likely to die of age-related illness. True, right? Okay, but not the point when you're looking at a study. So don't be misled, okay, by something that's not really the point. All right, second one here, should we scare the opposition by announcing our mean height or lull them by announcing our median height? One really tall person, the mean's going to be highly influenced by that, the median less so, okay? So you need to make sure data is being presented appropriately. And then the bottom one, science says 4 out of 5 people suffer from diarrhea, and the little boy says, does that mean 1 in 5 people actually enjoy it? Okay, so make sure you know what your comparison group is. Okay, when you say something's more or less than something else, you need to identify what that something else is. All right, so I mentioned in that last bullet point there that we didn't know whether or not something was statistically significant or whether the groups were truly different. Okay, so this is where probabilities come in. When we use inferential statistics, probabilities are important. All right, so the probability, which we see in a paper, is either P or alpha, and there is a difference between them, but I'm not going to get into that here. It's essentially the same. Each test statistic value, so a T, a statistic T, or an F, or whatever it is, will have an associated probability. Okay, so you do this on a computer. The computer spits out a T value, and it spits out a P value. Okay, if the P is less than 0.05, we consider the relationship or difference statistically significant. Okay, everybody's pretty familiar with that general rule, right? Okay, so what does that mean? It means that the chance of this finding, if the groups are equal or the variables are not all related, is less than 1 in 20. Okay, so this is the amount of error that's generally acceptable in statistics. Okay, we say that we're okay with being wrong 1 out of 20 times. Okay, that's what P less than 0.05 means. All right, so some common statistics. All right, all of these are going to tell you if the groups differ significantly or if factors are significantly associated with one another. So this is the basis of inferential statistics. All right, so let's start with T and F tests. Okay, T test will tell you if the means of two groups are significantly different. Okay, an F test will tell you if the means of 3 or more groups are significantly different. So 2 groups, they use a T. 3 or more groups, they use an F. And the analysis that gets you an F is called an ANOVA, if you see that term. Okay, so T and F are used when you're comparing groups on a continuous outcome variable. Okay, does anybody know the name of that type of inferential statistic when you have a continuous outcome variable? Heard the term parametric before? Okay, these are parametric statistics, continuous outcome variable. All right, so great, but all data doesn't come to us continuous, right? We have groups a lot of times. We want to know the percentage of babies that are low birth weight, for example, for 2 different groups. Okay, so that would be a category. In this case, we often use a test called a chi-square. Okay, this tells you if 2 groups with categories are related, or if 2 groups or more differ on the percentage of time they fall into different categories. Okay, so you can compare 2 groups, but this time our outcome is grouped as well. Okay, for a chi-square, it doesn't matter if your predictor has 2 groups or more than 2 groups. It works in either situation. Okay, there's a special type of chi-square or a special situation when you use something called a Fisher's exact test. You may see this in the literature. The mathematics is very similar to a chi-square. You get the same kind of output. It just works a little better when the sample sizes are small. Okay, so that's the difference. All right, so here's our table 1 again. Okay, the table I gave you actually had 2 more columns, so now you can see the other 2 columns. All right, so second to last column there is the T or chi-square value. Okay, they have to do both because some of these outcomes are categorical and some of them are continuous, so they use the appropriate test depending. All right, truly the column you're going to be most interested in is the p-value, right? That's what's going to tell you whether or not your groups differ significantly. All right, now I left it out, and so the table wouldn't be really cluttered, and this is just an excerpt of the table. Sometimes there's a number in parentheses after the t-value. You may have seen that before when you read papers. That's what's called the degrees of freedom. It has to do with the number of subjects that were in the study. Not all that important for your purposes, okay? So you really don't need to worry about that, which is why I left it off. All right, you can also relatively compare the p-values. So the smaller the p-value, the more highly significant the difference. Okay, do not compare the t and the chi-square values because those are influenced by other factors. But you can directly compare p-values. All right, so does anybody want to give me a statement from this? Okay, somebody back here said that maternal age at delivery, they were pretty similar. Is that true statistically? Is that less than 0.05? Okay, not less than 0.05. So we would say that the two groups are not significantly different on maternal age. Okay, anything else you notice? The what, which one? Yes, birth weight. Okay, so let's look at birth weight. Okay, so here's birth weight. We have 3151 grams for controls, 2708 for the heavy exposure, and look at the P. Okay, that is considered highly significant. Okay, way less than 0.05. So we would say that the control subjects are significantly heavier in terms of their birth weight than those with the heavy exposure. Okay. All right, so let me give you a few ideas of some things we can say. All right, so women who drink heavily during pregnancy and women who did not differ significantly by age. Okay, we said that already. Women who did not drink during pregnancy were significantly more likely to be married. Second one, that P is significant as well, right? The 0.008. So the P will tell you if it's significant, but you have to look at the actual values to know which group is higher or lower. All right, while women who drank heavily were also significantly more likely to smoke, among those who smoked, the two groups of women did not differ in the amount they smoked. Okay, so we see a big difference in terms of whether or not they were cigarette users right here. Okay, but the next row is looking at number of cigarettes per day. So if they did smoke, there really wasn't any difference in how much they smoked. Okay, so that's what that's telling you there. All right, gestational age at delivery did not differ significantly between the two groups. However, there was a non-significant trend. Have you ever seen that term in an article? Okay, so a non-significant trend for babies born to women who drank heavily to be born earlier than babies born to women who did not. So let's look back at gestational age. All right, 39.1, 38.5, not a big difference, okay, clinically speaking. Okay, 0.053. Okay, that is not less than 0.05, so we're not going to call it significant. But what often you will see in papers is that if that p-value is between 0.05 and 0.10, we'll start talking about it as a trend. Okay? Maybe appropriate, maybe not, depends on who you talk to. It's certainly okay if you have small sample sizes. Okay, and I'll get back to that issue in a few minutes. But when you have small sample sizes, you're less likely to find p-values that are significant. So in that case, you might start talking about these trends, because if you had more people, that difference might have been significant. All right, and then finally, compared to babies born to women who did not drink, babies born to women with heavy alcohol exposure were more than 4 times as likely to be low birth weight. Remember, we said that, and we showed just the first part of the table. And this difference was statistically significant. So now, because we have p-values, we can start talking about whether the groups are truly different. All right, questions so far? We good? All right. Okay. All right, so here's another table one. Okay, this is from a different paper, also just came out in Pediatrics. And here, look at the title. They are comparing characteristics of preterm and term infants with neonatal diabetes. Okay, so the focus here was on neonatal diabetes and the differences between the babies who were born before 37 weeks and those born at 37 weeks or later. All right, so what can you tell me here? Actually, what's different about this table that you didn't see that was different from the last one? Are we missing a column? We've got P's, but we don't have any T's or chi-square. Okay, sometimes that's how people present their data. Okay, obviously Pediatrics is a journal that will allow you to do that. Some journals will not. Some journals require you to put the T's and the P's, the T's and the chi-squares in. Okay, for your purposes, did you really care what those values were? No, right? Okay, so the P is all that matters to you. We're drilling down to what's important. All right, so what conclusions can we draw here? Do we know what those values in parentheses are? Remember, before we had the plus or minus to do a standard deviation. What are those? Okay, so if you don't know what something in a table is, go to the footnote, right? Footnote says the data presented as median and interquartile range. Okay, so we don't have means here, we've got medians. So they had some distribution issues with their continuous variables. All right, anybody want to give me a statement here? How are babies born less than 37 weeks different from babies born at 37 weeks or later when we're talking about babies with neonatal diabetes? Okay, who's bigger? No surprise there, right? All right, birth weight centile, that one's a little interesting, okay? So there we've got weight for gestational age. We see it's actually reversed. Okay, so the babies that are in utero longer are more likely to be growth restricted, okay, when there's diabetes involved. Okay? All right, so here's some things we can say. So the typical term infant with diabetes is not diagnosed until 6 weeks, while the typical preterm infant is, the term infant is at 6 and the typical preterm at 1. Okay, see that from the second row? 6 versus 1. All right, you noticed that I said typical. Okay, we need to be careful here. You could say the median age at diagnosis was 6 weeks versus 1 week, but don't use the term mean or average or say on average, because these are not averages. These are medians. Okay, so be careful in terms of how you interpret it. Okay, so we can also say the difference is statistically significant, right? Because we had that right there, highly significant. All right, there's more variation in birth weight centiles for preterm infants than for full-term infants. Where did I get that? I think somebody said the interquartile range. Okay, so right there, there's bigger variation there, 1.2 to 34, then 0.5 to 16. Okay, so you can draw conclusions about variation as well, if that's of interest to you. All right, moving on. F-tests. So we use F-tests when we would otherwise use T, but we have more than 2 groups. Okay, in this paper, we have 4 groups. All right, so this is from a paper that is looking at the fetal alcohol growth restriction again, but now they're comparing 4 groups in their sample, and they're looking at their growth trajectories. So 4 different growth trajectory groups. Okay, and they're comparing them on whether they had different rates of alcohol exposure in utero. Okay, ounces of alcohol per day and days that they drank per week. All right, so what can we say? All right, you notice here there's no p-values. We need p-values, don't we? No, why don't we need p-values? They're at the bottom, right, okay. So, look at here. We have little asterisks. Those mean something. Those mean that p is less than 0.05. So a lot of times there will be shortcut. Don't put in the p-value. Just put in what they're less than. So you might see 1 asterisk for p less than 0.05, 2 for p less than 0.01, and here we have 3 for less than 0.001. All right, somebody give me a statement here. What can we say about the group, the growth trajectory groups, related to the amount of alcohol exposure they had in utero? About ounces of alcohol per day. What's that significant F tell us? Guesses? Go ahead, Dr. Wood. I know you want to say it. There you go. Exactly. All right. So what's important there is what he didn't say. Okay? He did not tell us which group had a higher level of alcohol exposure. He only said, on average, there's a difference between the groups. Because what you have here does not tell you which groups are significantly different. It only tells you overall that the 4 groups are different. Now, we could make some assumptions. Okay, we probably, if this is significant, probably means that the 1.2 and the 0.3 are significantly different. Okay, but we don't know for sure. Okay, what we're missing here is something called a post hoc test. Okay, post hoc tests make pairwise comparisons among the groups and let you know which ones are significantly different. Okay, they didn't tell us about that here. All right. This is what you want to see when you have an F-test. This actually presents the post hoc test as well. All right, so this is from a different paper in Pediatrics this month, looking at different dosage schedules for pneumococcal vaccines for newborns. And in particular, was this preterm infants? I'm trying to remember. Yes, preterm infants. Okay, so without going into what the differences are, just there's 3 different vaccine dose regimens here. All right, so as you can see, they're looking at the differences in terms of the serotypes 1 month after the primary final vaccination. All right, so this is kind of interesting because they're giving us proportions and they're giving us the 95% confidence interval. Okay? So they're telling us essentially the range for 95% of those babies. All right, so what do we learn here? Okay, what's going to be really important, see these little letters right here? Okay, that actually tells you which groups are different. So if you look down here in the footnote, you would definitely need the footnote for this table. Okay, if there's an A after it, right there, what it means is that the accelerated and extended schedules differ significantly on that serotype, okay, at p less than 0.05. So there's a lot of information crammed into this table by the use of these footnotes. All right, look at this one right here. There's a C and then there's an asterisk. So what that means is that the reduced and accelerated schedules differ significantly right here and right here, okay, but it's at p of 0.001. All right, so see how nicely this table gives you a ton of information in a little bit of space. Okay. But you need to be careful. You need to make sure you understand, read the title first, read the footnote so that you know what's involved. All right, so let me show you a few statements that you can make about this table. Okay? Infants who received the accelerated schedule had significantly lower rates of protective antibody concentrations for serotype 1 than infants who had extended vaccination schedules. So accelerated, extended, serotype 1. Accelerated, extended. So what that means is the 0.80 and the 0.94 are significantly different. All right, second one. Infants who received the extended schedule were nearly 4 times more likely than those who received reduced dose to have protective antibodies for serotype 6b, and this difference was highly significant. Okay, so we've got 0.20, 0.78, almost 4 times higher, right? Okay, and it was highly significant. We know this because we have this little asterisk here. Okay, so again, that's comparing relative p-values. When we get to p of less than 0.001, we start to talk about something being highly significant. All right, questions on this? Just taking it all in. All right. All right, on to something else. All right, a lot of times we don't just want to know if the means are different. We want to know how much they're different. Okay, so I was hinting at that by giving you about 4 times. Okay, odds ratios allow you to quantify that difference. Okay, so they will actually tell you how different groups are. Get caught up here, make sure there's nothing else I need to absolutely tell you. All right. So odds ratios, denoted as OR, tell you the increased likelihood of an outcome associated with a particular group membership. Okay, these, instead of using p-values, so we had p's with our t's, p's with our f, okay, they use confidence interval, typically a 95% confidence interval. That's the same thing as a p less than 0.05. Okay, so we say that a confidence interval is significant if the confidence interval does not include 1. Okay, I'll give you an example of this in a minute. Let's do this one here, and then I'll give you a table. All right, so the odds ratio for males for ADHD is 3.0 with a confidence interval of 2.2 to 3.9. Okay, so what that means is that males are 3 times more likely than females to have ADHD. That's how you interpret an odds ratio. Okay, so it's the times, the amount, the multiplier essentially for the difference between the groups. All right, so is that increased rate significant? Sure sounds like it, right? 3 times more, you'd think that would be significant. And in fact it is, because the confidence interval does not include 1. Okay, and the key about the confidence interval including 1 is 1 would be an equal likelihood. Okay, you would have an odds ratio of 1 if the groups were equally likely to have ADHD. So if your 95% band of confidence includes that value of 1, we have to say that that odds ratio is not significant. But in this case it is. Okay? All right, so here's a table with some odds ratios. All right, so this one was looking at hospitalization for influenza A versus B. Just came out in Pediatrics again. Okay, so they're comparing the symptoms, the sign or the symptoms in the children who had seasonal A versus influenza B. Okay, so in the first two rows here, we have the number of children in those groups that are reporting those symptoms and the percentages associated with them. Now we have very unequal groups here, so the ends are not all that helpful to you. You're going to want to look at the percentages or you're going to get confused. All right, so let's take, for example, the first one. Okay, we have 92.9% of those with seasonal A had a fever, 93.5% of those with influenza B. Okay, our odds ratio is a little greater than 1, 1.1, but because it includes 1, it goes from 0.83 to 1.46. We would say that that is not an increased likelihood for influenza B. Okay, that is different from headache. Okay, so those with influenza B, 9.9% had headaches, 3.6% for seasonal A. Odds ratio is almost 3. Okay, does not include 1. So we would say there's a significant difference that those with influenza B significantly more likely to have headaches than those with seasonal A. Okay. All right, so a few more statements. Okay, did not differ significantly in the rates of fever, cough, wheezing, or vomiting, diarrhea. Okay, so those were all the ones that were not significant. Okay, compared with those who had seasonal A, children with influenza B, as I said, were 2.8 times more likely to have experienced headache. All right, now there's a few ways you can say this. You can use the 2.89 as a multiplier. You can talk about an increased percent. So once you hit 2, you've increased by 100%, right? You have an odds ratio of 1, equally likely. Your odds ratio gets to 2, you've increased by 100% your chance. Okay, so you always have to subtract 1 in order to actually talk about it as a percentage. So 2.8 times more likely means an increase of 189%, or we could just say are almost 3 times as likely, and this increase rate was significant. Okay, and then finally, compared to those with seasonal A, children with influenza B were 12% less likely to experience wheezing, but this difference was not significant. All right, let's take a look at this one. Right here. All right, not significant. Confidence interval includes 1. All right, why did I say 12%? Not 88%. Somebody said it. What was that? Okay, the key is the difference from 1, right? As you move further from an odds ratio of 1, you're increasing the likelihood of group differences. So when we're over 1, it's very easy. That number's our multiplier. When we're less than 1, we actually have to subtract that number from 1. So we've moved 12% from that odds ratio of 1 of an equal likelihood down to 0.88. Okay? So if the odds ratios are less than 1, you subtract that number from 1 to get your multiplier. All right, now typically we would not interpret an odds ratio that is not significant, okay? But I wanted to demonstrate how you interpret those that are below 1, because we didn't have any that were significant here. All right. Okay, any questions on odds ratios? Right along. All right, so you may have noticed, or you may not have, in the final column, look at the word in front of the OR. It says unadjusted. Okay, what does that mean? Any ideas? All right, we typically say that analyses are unadjusted when it's just the relationship between two variables. You're not considering anything else. Okay, however, in reality, there's often things we do need to consider. Okay? So in this case, we adjust our group differences statistically in order to account for those factors. All right, so often this is done with a regression analysis. So we have a multiple regression where we have outcomes that are continuous, or a logistic regression where we have categorical outcomes. All right, so since regression was not listed as one of those things that appears frequently, it only appeared in 18% of the journal articles that were reviewed, I'm not going to go in depth into regression analysis. But what it will give you is something related to odds ratios, which I think is important to know, and they did identify that in the papers. Okay, what the regression will give you is an adjusted odds ratio that tells you how much the groups differ after you've statistically controlled for other variables or removed variance due to those variables. Okay, regression analysis will also give you information about how much variance is accounted for in your outcome from your predictors. That's a multiple R squared, and you can get correlations or R's between variables, but we don't have time to go into that. All right, so here's a table with odds ratios that you just saw, but it has the actual final column that was in the paper. Okay, so we have our unadjusted odds ratios, and then we have our adjusted odds ratios. All right, so what's different in the final column? What did they adjust for? Okay, always go to the footnote if you're not sure. Adjusted for age and health status. All right, if you go to this paper and look at their table 1 that compares group differences on background characteristics, what they found is that the children with influenza B were older and more likely to have existing health conditions. Okay? So because of that, we want to make sure that any conclusions we draw about differences in symptoms are truly related to the flu and not related to differences in reporting due to age or health status, or differences in their underlying health conditions. Okay, so statistically, we can run an analysis that will take that into account. Okay, this is what gets us the adjusted odds. So this tells us the increased likelihood after we remove possible group differences for other factors. All right, so why do you suppose there's no adjusted odds ratio in 4 of those rows? What do all those have in common? Not significant. So the unadjusted odds ratios were not significant here. Includes 1, includes 1, includes 1. Okay, so if your unadjusted odds ratio is not significant, typically you don't run an adjusted analysis because as soon as you start removing variance, you reduce the likelihood that you're going to find an effect. So you will almost never have a situation where an unadjusted odds ratio is not significant and an adjusted odds ratio is. It just, in practice, happens rarely. So typically we don't even bother to adjust and run additional analyses if the groups are not different before we adjust for anything. All right. So that's what that says down there. All right, so a couple things we can conclude about this table. Okay, after controlling for age and health status, children with influenza B were significantly more likely to experience headache than children with seasonal A. Okay, so we had our unadjusted was significant and our adjusted was significant. Okay, that confidence interval doesn't include 1. All right, after control for significant confounders, children with influenza B were 38% more likely to experience abdominal pain than children with seasonal A. This was a significant difference. Okay, right here, 38%. Confidence interval does not include 1. It's close, but it doesn't include 1, so it's significant. All right, last one. While children with influenza B were more than 2.5 times more likely than children with seasonal A to experience arthralgia, the difference in the rates between the two groups was no longer significant when child age and health status were controlled for. So if we look back, this is a case where we have an unadjusted odds ratio significant and an adjusted odds ratio non-significant. Okay? So what that means is that the differences that we found in the unadjusted analyses were likely due to underlying health status and age differences. Okay? Truly wasn't a difference in the type of flu they had, but was related to their underlying or background differences. Okay, with me so far? Yes? All right. Okay, final comment about statistical analyses, the issue of statistical power. I mentioned this earlier. Okay, so the mathematics behind test statistics result in sample size playing a big role in whether or not effects are significant. If your sample is too small, you may find that very big effects are not significant. Okay, you might find 10% versus 40% on something and that not be significant if your groups are small. Okay, so whenever you see a study where there are no effects, they didn't find anything related to anything else, you should always question whether or not their sample size was big enough, did they have enough statistical power. They truly should be telling you that when they describe their analyses. Okay, second thing here, a very large sample may result in effects being statistically significant that are not clinically significant. Okay, so we have to interpret this with caution as well. Really good example we see in the adult literature right now is all these studies on different diets. And they have these huge sample sizes, and they find that this diet leads to a weight loss of 3 pounds more than this other diet. And we've got 2,000, 3,000 people. That 3-pound difference ends up being statistically significant. Okay? But is it clinically significant? Are you going to really recommend one diet over the other for 3 pounds? Okay? So you have to really interpret with caution in terms of, is this clinically significant? And that's where you have to use your clinical judgment to make that decision. Okay? Good example here is the arthralgia in the flu study, and I'm going to show you that here in another way. All right, so the last thing here, we have the epidemiology concepts. Okay, 3 things I want to hit real quick. All right, so have you heard about risk reduction and risk reduction statistics? Yes, okay. All right, so there's 2 different ways at looking how good different treatments or interventions do when you compare them, or how one disease state is worse than the other. Okay, so first of all, we have the absolute risk reduction. Okay, here's how you calculate it. You subtract the lowest from the highest percentage, looking at the incidence in one group versus the other. All right, so if you look back at that table, comparing influenza A and B and the arthralgias, okay, for influenza B, the rate was 1.2. Okay, for A, it was 0.5. Okay, so the absolute risk reduction, you simply subtract them. It's 0.7. What that means is 0.7% fewer children with A experienced arthralgia compared with children with B. Okay, doesn't sound real big, right? Even though, remember, it was significant in the uncontrolled analyses. Okay, so absolute risk reduction is the absolute difference between the risk for each group. All right, this is different from the relative risk. Okay, so relative risk reduction is 1 minus relative risk. And then here's how you calculate relative risk. I'm not expecting you to be able to calculate this necessarily when you walk out of here. I'm showing you the math so that you understand why they're so different. Okay? All right, so if we calculate relative risk, we actually get 58%. Okay? So the absolute risk reduction was 0.7%. The relative risk reduction was 58%. And both of these statistics could be published to talk about the differences. Okay, so the numbers can be very, very different. And the reason is because the relative risk is based on proportions that don't take into account how rare something is. Okay, so a big reduction in a rare event is still a rare event. Okay, so we have to take that in mind. One place you always need to keep that in mind is in pharmaceutical research. Because pharmaceutical research, they're trying to tell you how great their drugs are compared to some other drug, and they use a lot of risk reduction statistics, and 9 times out of 10, they are telling you relative risk reduction, not absolute risk reduction. And so you need to read very carefully to understand, yeah, this may be a huge percentage, but is it clinically significant? Okay? In this case of that I just showed you about influenza A and B, no, probably not. That's not really a clinically significant difference. All right. Couple things, other real quick, measures of disease frequency, terms incidence and prevalence, right? We've all heard those? All right, are we comfortable with those? Okay, good, I like to see that. All right, so incidence is the number of new cases. Okay, so when we look here at a practice of patients with fibromyalgia, sorry, this one was an adult one, okay, we find about a 1% incidence, so new cases, okay? Very different from the flu, looking at people in Tennessee, of the percentage of people that get the flu every year, we have about 15%, so that's incidence, new cases. All right, prevalence is different. This is the existing number of cases. So for a chronic disease like fibromyalgia, we're looking at making sure we include the new cases plus the existing cases. Okay, so in that case, the prevalence is going to be much higher than the incidence. All right, so if we look at the flu, however, okay, look at that, much, much smaller. All right. Prevalence, sometimes called point prevalence, if that helps you remember. Okay, it describes the current burden of a disease in a population to facilitate planning and resource allocation, so from a public health perspective. All right, so take a look at this. These are the differences. Look at the incidence and prevalence rates. And the difference here is whether we're talking about a chronic condition, okay, or an acute condition. Okay, anything that lasts less than a year will have a higher incidence than prevalence. Okay. So it tends to be that prevalence is more useful when we're describing chronic disease, so we care about everybody with the disease, just not just the newly diagnosed, while the incidence is much more useful when we're talking about a short-term condition. Okay, so public health, when we talk about flu, when we talk about Zika, some of these other things, okay, you're going to see incidence statistics. Okay, so that's the difference and why. All right, nice little graphic here. I use this with my biostat students. I teach the biostats class for the first year medical students, so I'm trying to bump up the knowledge in medical schools of biostats, that thing I showed you on the first slide. But this is something they really liked in terms of helping you remember. So prevalence is all the water in the tub, the incidence is coming in, and then we talked a lot about how mortality rates and recurrence rates affect those statistics. So anyway, nice little graphic. All right, last thing. How well does a diagnostic test perform? Sensitivity and specificity. We comfortable with those? Kind of. All right, so real quick in 60 seconds here. All right, sensitivity is the probability of testing positive among those who actually have the disease. All right, probably when you took your biostats class in medical school, you had to calculate a whole bunch of these, right? All right, not going to make you calculate, just want you to understand. Okay, so specificity is the probability of testing negative among those who do not have the disease. All right, so an example, data from a study published in the Journal of the American Board of Family Medicine looked at the accuracy rate of rapid strep testing in those who had had a recent strep infection. Okay, so how well is it picking these people up? All right, sensitivity was 0.96, specificity 0.91. Okay, always ask yourself when you read a paper that's reporting sensitivity and specificity, what's the true disease state they're comparing it to? Okay, there's got to be some sort of gold standard. In this case, it was a laboratory culture. Decent gold standard, right, for this kind of test? All right, so what does this mean? Ideally, we want a test to have sensitivity and specificity of at least 0.9. That's generally considered a good test. However, it's a trade-off because typically when one goes up, the other one goes down. So we have to find that point where we have a good balance. Okay, we also consider whether it's a screening test or a diagnostic test. For screening tests, we want to get everybody, right? We want to make sure that we don't miss anybody. So in that case, we want sensitivity to be very close to 1. And this is different from a diagnostic test, a follow-up test that you would use, where you want to make sure you're not saying somebody has the disease when they don't. So in that case, we want our specificity to be close to 1. Okay, but in both cases, you don't want the other statistic to be too far out of balance. All right, so back to the example, sensitivity 0.96, specificity 0.91. Okay, sensitivity means that 96% of the people with the condition will be identified with the test. So they were picking up 90% of those with recent strep infections with their rapid strep test. Okay, conversely, they're only missing 4%. They only have a 4% false negative rate. Okay? Then the specificity means that 91% of people who do not have the disease will be negative on the test. Okay? So we have a 9% false positive rate. All right, so in your opinion, is this a good test? 0.96 specificity, 0.91 sensitivity, that's a pretty good test. All right, would it be better for screening or diagnosing? Screening, because the sensitivity is higher. You would have 9% of people that you're finding saying have the disease when they don't, not necessarily the best in a diagnostic test. All right, that was stats in 55 minutes. All right, questions? Heads are spinning, right? All right, well, these slides will be available to you, I'm guessing, Dr. Toole. Will they have these slides they can access? Okay. All right. So if you think some of this information might be helpful to have when you are reviewing journal articles, we can get that to you. My email address is on them. If you have any questions, happy to help. All right. Nothing else? All right. Let you go.